Hello, everyone. My name is Saeid, and I represent the National Institute of Engineering and Technology in the UK. I'm going to steal 1 minute of my presentation time to give you a brief introduction to what the National Institute is. You may have heard about Dyson, Sir James Dyson. So in 2017, he was meeting with the Ministry of Education, and he criticized the Minister of Education that you are not providing the right engineers for the industry. And so the response was, why don't you go and make your own university? And that's what he did. So we are a university on the factory floor, and we have just recruited our 9th cohort this year. So our students spend 2 days in learning in the institute and 3 days in the industry side. So when they finish, they are actually like graduates who have already done a graduate job as well. This first presentation that I will have today is on a PhD project which was based on Coventry University, and I was jointly supervising that with Professor Zhang and Dr. Evangelos Apostolopoulos, who just recently graduated, was a PhD student on that project. So the project framework is towards digital twin development for space applications. And as we know, lightweight is a very crucial parameter when we deal with the space components. And part of that project was to look at the struts, which are a crucial part in landing and in takeoff of satellites or the space vehicles. So the title is Influence of End Geometry and Defects on Structural Integrity of Lightweight Composite Struts. And the struts that we have been using in that was manufactured, fabricated by space structures that we would like to acknowledge them as well. The project was also sponsored by National Physical Laboratory of Library of UK and the European Space Agency. So it was a fully funded research project. I start with, after that introduction, with the aim and objective of this particular part of the project, which was to investigate the impact of geometrical features near the end of the strut on the failure behavior and also the load carrying capacity of the struts. The idea with regard to this aim is that we expect the buckling mode to be the predominant mechanism of failure for struts, but something else might have happened. And we also found evidence from NASA experiments that they actually strengthen the transition zone of the struts significantly to make sure that the failure mechanism will be buckling and not something else. So the way to deal with this was to develop a suitable tool to predict the strut performance under static compressive load, which is the one that is of interest, and evaluate and implement non-destructive inspection testing to inspect and sense and find a way, because in the concept of digital twin, it's very important to be continuously monitoring and comparing and feeding back to the system, and real life monitoring of structure is very important. And to conduct testing for the struts to validate and see if we can match that with numerical methods. So to start with the specimen and challenges that we faced, quantification load that we used was 4 kilonewton. The composite struts got a carbon fiber reinforced epoxy material, which had 2 layers, a unidirectional and a development plus minus 45. Unfortunately, I can't go much into details of the structure and details of the composite because of the IP rights of the sponsors, but this is the general dimensions and the shape of the ends. And as you can see on the right, the 2 layers thicknesses. Challenges was to identify the failure modes and predict the failure behavior by doing fine element analysis. So we obtained 3 different samples from space structures. One was in the as-received condition, one had a longitudinal crack on it, and one had a delamination between 2 layers. And this is an overall show of that what so that's the pristine one. That's with the longitudinal crack, which you can see on the image observation, and that's the delamination within the 2 layers. And they had all the same geometry, only the difference was these defects not induced but measured in the compound. The testing methodology is, as you can see, under compression, because tension was not viable. When the tension test is acting, actually the insert on the tops go up, and the main application is also in compression, so we focus on compression tests. We use a combination of image correlation and fitting strain gauges at the appropriate locations on the specimens, depending on whether they had a defect or not. And then we use them in finite element modeling later to validate. The strain gauges were near the transition zone, as you can see, and crack opening, delamination. We use DIC for capturing failure mode, and load reading and from the testing machine to see how the components perform. And this is the arrangement of strain gauges. Strain gauges were fitted in hoop and in axial direction at different locations, as you can see on different specimens. This is on the struts with a longitudinal crack. As you can see, there are the strain gauges in there slightly away from the transition zone, and in the axial direction very near to the transition zone. Also 3 strain gauges fitted around the transition zone, as you can see in the axial direction as well. And this is the third one, which has a delamination. Again, strain gauges in both directions near the end of the delaminated area, and the strain gauges at the other end, which are used to monitor what happens at the interface for the transition region. So that's what how we set the strain gauges. Data collection was by the load machine, which was done. Part of the experiments were done in Holland in ESA, or the European Space Agency lab in Delft University. The strain field and by digital image correlation was measured. The strains at the specified locations were recorded, as you will see in the images shortly. This was the testing machine where the component was put for compressed load, and then you can see the spectrum pattern printed by a special printer that they have, and also the DIC image of the strain field under compressive load. You may notice that there is a small insertion there like a hole. That is requirement for fabrication, so we have to have that to be able to manufacture those struts. The first observation of load versus displacement for the 3 samples, as you can see, the purple one is the as-received one, and the second one is the one, this black line is the one with the longitudinal crack, and the third one, which is the blue one, is the one that had delamination. As you may see, more or less, the scatter between the failure loads is not that wide, so they are all around somewhere between 11 and 12 in the near term. And the observation of that was a slippage of the recording machine. So that was recovered by the machine direct. So that's not a significant point to mention. And those are the first load drops, which there's a sudden drop, and we will see that in the images, how we can explain that. All three struts failed suddenly, as you can see. First load drop was due to jig slipping in the second strut, and the struts show minimal difference in failure loads, as I mentioned. These are the image, the images of the failed components, as you can see for strut 1, which is the initially undamaged, and that is the area where the damage started and it failed. There was a sudden drop of load, and this is on the second strut, which has a longitudinal crack. So what we can conclude from this is that initial defects didn't really have a great impact on the failure load. So we went on to look at the strain data, based on strain gauges for different specimens. This is for strut 2 with longitudinal crack. As you can see, the transverse strains and the longitudinal strains. The difference in those on the longitudinal strains can be explained by 1, 2, and 3 are around by the vicinity to that hole, natural hole, or vicinity to the position of the crack. So they should actually be matching if it's a very accurate one. And sensibly, this one, which is away from the transition zone, showed less longitudinal strain. And as expected, the transverse strains for 5, 6, and 7 are more or less the same. So no opening of crack was captured by the gauges. Gauges near the transition zone showed higher values. And the conclusion from this one is the gauge data along with the IC data prove transition zone is critical. For strut 3, we did similar analysis, and you can see the findings of that. And if I move on, and the features that we can identify in this one is for the transition zone, transversal strain gauges show higher values compared to the longitudinal ones. And the conclusion is that the transversal strains concentration on the transition zone in combination with the lower transversal properties of the layout is the guiding force for failure. FA modeling was done to verify the results, and these are the boundary conditions. It was done in Abacus and by using the sub-modeling, so making sure that the time of analysis is optimized. And these are the details of the model. We use Xiang damage model to in the final judgment analysis by looking at the tensile and compressive properties of the matrix and the fiber, which is a relatively challenging thing to set up, and the homogenization approach was used to set the material parameters, but the mechanical response is in different directions for different layers, different as we expect. And the validation of finite element against the experimental data is presented in this slide. As you can see clearly, the model created proposed a very good match. And conclusion from this one is that the model is considered valid up to failure. But as you can see, beyond the failure, there are challenges. The stiffness of model agrees with experimental data, model agrees with failure load, and model struggles to capture post-failure behavior. Different fracture toughness values for each layer used. Failure load and modes. Consistent. This is what I can take from the finite element against the experimental results and the range of loads that you can see 12.6 with a variation of 9 and 13.8, and the difference is 9%. And we come to conclusion. That is what we can make out of this observation. As I said, this was a small part of the PhD work, which provided an insight to the fact that if we are going to make sure that buckling is the critical mode of failure for this kind of components, we need to be careful with the transition block. Thank you very much.